roundtable discussion about fundamental physics. So I hope we will learn something this afternoon. So our panelists are Alessandra Buonanno, Katherine Freese, Donoghue, Frank Wilczek, and Gerard Hooft. And they have prepared slightly different presentations. So we will first go to John, Alessandra, and Katie, and then our two Nobel Prize panelists have decided to look at all the questions that were posted on the website and answer all of them. And so later we will go through all these questions. Everybody will be able to comment. So let's start with Alessandra.
Okay, so we were actually asked to prepare 5 minutes of a presentation, so I just have one slide, and I put there a summary of what I thought could be areas where we might expect some paradigm shifts in gravitational wave astronomy. Of course, paradigm shift is a big word in the sense that maybe it will not be a paradigm shift, but will be something interesting, new discovery. So let's start. We are probing the nature of the compact objects that we are discovering. So some of them, actually the majority of them, seem to be dark. So we think they are black holes, and we are trying to test the hypothesis of being black holes, in particular the black hole solution in general relativity. Are they a black hole or not? And there have been many ways in which this has been, continued to be tested. And I wanted just to make an example. So people have proposed in a phenomenological way, if there is not an horizon, but it's a surface which is not just absorbing 100%, but reflecting, one could see after the merger what people call echoes, which are these gravitational waves that are trapped between the potential outside the black hole and the surface of the would-be black hole, and then they leak out from the potential and create these echoes. This is just one example. One could also discover completely new astrophysical objects. This happened even in general relativity. This happened in other fields, in electromagnetic astronomy over the years. People have discovered even neutron stars that were not known, right? Pulsars, and so maybe we discover an object without violating general relativity, but it's a new object that we have never seen before. That's possible. Then more in general, besides the nature of the object, but whether numerical relativity could be violated during the whole process of the in-spiral, the plunge, the ring down, etc. And this is something that you heard from my talk, and also this morning, the talk by Mary. These are things that people are trying to understand and test. That will be also, of course, an important, a breakthrough if that would happen. I also tried to emphasize at the end of my presentation that we have not found any anomaly until now, but if we found an anomaly, we should also check that the anomaly is just due to mismodeling or systematics, right? Systematics, they are very important. So before concluding that this is really an anomaly that would lead to something completely new, we should check that it's not due to not including all the physics in the waveform, or environmental effects, other effects that are there due to other bodies or the environment, before concluding that it's really something completely new. So then another bullet point here concerns cosmology, because with gravitational waves you can have an independent measurement, independent from electromagnetic astronomy, of the expansion rate of the universe, or even the dark energy, And then here I also have dark matter. With gravitational waves, you can look at imprints in the gravitational wave due to dark matter in form of ultralight bosons, but also other kind of dark matter that can interact with the objects gravitationally and can have an imprint again on the dynamics and then the waveforms. Then discovering primordial black holes. So we talked a bit yesterday about the smoking gun if we were observing subsolar mass compact objects, because it would be hard to explain them as objects that come from the collapse of stars. And then probing the composition of neutron stars that one can do with gravitational waves. Maybe that also will bring some novelty, something that we unexpected. Or maybe we'll just clarify the composition without any surprise. And finally, although this is quite important, detecting gravitational wave from the early universe, the stochastic background from cosmic inflation or phase transition, cosmic strings. This is more for the future because the current detectors do not have the sensitivity to see these signals, unless, for example, the stochastic background from inflation has not a red slope but blue, and some people have predicted, and maybe in some model this can happen. This might be more for the future, not even LISA or third generation detectors, but post LISA mission. I mean, the field just started, so there are many decades and centuries from now. So at some point we will see these also signals, and maybe we will discover something that we have no idea today. So that's it. That's the list I put together.
Thank you. So join us. So basically, join is next.
I want to just start with a panel discussion that actually had some effect on me. I started researching in '74, and I was probably reading this panel discussion from 1971 about a year later, so 4 years after the discussion. And the panelists were distinguished physicists of the time. And it was interesting to see what they thought of the next decade would be when I had half of the information. I had 4 years of information. And the first 9 pages of this was about Vegas saltpeter equations and triple Reggie couplings, Reggie theory. This is Francis Lowe here talking about the triple Reggie coupling. And to be fair, Feynman started giving him a hard time about this is some of the same old discussion, more trouble, more powerful troubles than before. In other words, it's more wrong. So Feynman is the only one who really came off nicely in this. But then if you look for what actually happened, you see very little. This is Dave Jackson talking about the fads. He goes, SU3, SU6, SW, PCAC, and some effective Lagrangians, duality, the Veneziano model. This is what was going on in the 60s. And he ends up with this thing that sounds like a winning suggestion. He says, I anticipate that the next year's fad is going to be Weinberg's Lagrangian. But what gets me is the audience laugh. And in addition, a little later on, this is Jackson still, he said quarks exist, there's a new scale, and thus Feynman zero mass quarks are impossible, let's say, and they laughed again. So people didn't really have a clue as to what was about to hit them.
Does it say in the transcript?
That's what it says right there. We're not laughter and shoot. I mean, these folks are very jolly. More jolly than we are. We don't laugh as much as they do. They laugh at all these things. So the lesson is that if you're sitting there looking at the hot things of the day, you're often missing what's about to happen to you. And sitting there in 75 after Versailles and after these two gentlemen made the theoretical breakthroughs and experimental breakthroughs at the time, it was clear that it was good not to pay attention to the panel discussion. Okay? If we had run this right before the LHC, it would also have been wrong. There was a powerful amount of groupthink in the theory community right before the LHC. And in both these cases, the deciding factor was the external input that projected us onto reality. And so one of the questions that we really should think about is, what are the experimental opportunities, because that's where we have a chance of seeing something, and what are our present versions of mistaken assumptions? There are some experiment has provided us with some things that need to be resolved. The variant asymmetry is one of them. It needs to be something that talks to the standard model, so because it produces variance. And so probably the simplest of the possibilities would be leptogenesis associated with lepton number violation at high scales. There's a need for dark matter or some resolution to the physics of dark matter. Here the simplest of options connected to the standard model is the axion, which also solves a conceptual issue of the standard model, which is a strong CP problem. I ended up putting the Hubble tension up there, even though I personally in the way didn't see this, but I think it was clear that the tension is strong enough now that the experiment may be the way to resolve it, but it's not ignorable at this stage. And then the theoretical imperatives, the UV gravity are also that. The experimental opportunities, Frank, in the middle of our first day's discussion, provided us with a list, and we all can expand on that. There's a lot of good experiments going on. Absent from Frank's list was the next generation LiDAR. So the interesting question is whether our standard pathway is going to continue, and given political realities and social realities, it may be that we don't. We've come to the end of that line of experimentation, but there are still other experiments that have potential to provide a lot of interesting information. So, I did want to just devote two things about assumptions that we make and I make, and just see if these might be fruitful ways to proceed. One of the lessons that I've taken away from the LHC results is that the unification pathway that we all feel is the way to go. May have evidence against it by the same reasoning that we thought there was going to be new physics at the LHC. So first of all, we haven't seen any gauge unification. The electricity magnetism was just the identification of the original gauge theory. The standard model isn't unified. It has three separate interactions, and there's gauge mixing, but there's not a unification. So we've never actually seen unification. The LHC has given us a hint that there's not much going that talks to this standard model. One way of interpreting it. So we used to think that we needed to find physics there because if you had high-scale unification, it would cause a hierarchy problem with the standard model, and so we needed protection, a naturalist protection at the weak scale to protect this hierarchy. If we don't do it, if that reasoning is logically consistent, if we don't have that protection, then maybe we don't have unification. So the pathway that we've been working on maybe is not the correct pathway. Maybe there are other interactions. If this could be one gauge interaction or 3, I can't do 4 or 5 or 6. There could be other interactions, not unified, but just separate. And one of the crazy ideas along this way is Holger Nielsen's random dynamics, which basically says that anything that can happen at high energies, the stuff that arrives at low energies is protected by symmetries. So chiral and gauge symmetries protect the physics of low energies. And so, SU1, SU2, SU3, maybe SU4. The next one is the beta function will be a little bit bigger. Anyway, so that's just one of the possible suggestions for one of our standard assumptions. And the other is to think about changes to quantum mechanics and quantum field theory. There really isn't any reason that we've seen for needing that. But nevertheless, there's a lot of processes that could, in principle, be a frontier for it. So in particular, macroscopic objects, where the interactions are fully macroscopic, could be a frontier. And here, I think it would be an interesting phenomenological project to try to suggest for experiment parameterizations of the possibilities for types of deviations that could occur, just so that we can have a sense of how well we constrain that frontier, much like parameterized post-Newtonian does for general relativity. For example, an idea is if we start our quantum field theory with a path integral, maybe we add some stochastic or dispersive terms to the path integral and see what they predict. They have coefficients, you found the coefficients. That's just a possible suggestion. But it's an area that is only lightly explored, in which experiment is being done, and which experimenters would likely be input. There's my contribution.
Thank you very much.
I guess my major comment is cosmology has been exploding. Since the turn of the millennium, we learned what is the total mass and energy content of the universe, which corresponds to the geometry of the universe, and the age of the universe. This precision cosmology, it's been an amazing time. And the data are still exploding. We have the James Webb Space Telescope, we have the Rubin Space Telescope, we have the cosmic microwave background experiments that are coming. Who knows what we're going to find? So to me, that's actually perhaps the most exciting thing I can say, which is we can't really talk about what we're going to find because we don't know. But in the meantime, from the point of view of a theorist, there have been some interesting tensions in cosmology, and the question is, what is their status? So I was going to report on that. We had a brief discussion of this, I guess, yesterday, which is that the DESI experiment looking at baryonic acoustic oscillations claims to find time dependence of dark energy. They parameterize the universe in terms of that equation, the W0 and WA, which is at redshift of 0 today, the value of a dark energy equation of state and its derivative. And if you do that, thank you. So in doing that, this is the cosmological constant, and they claim to be away from that. And they're using, in addition to their own data, they're also using CMB and supernova data. But I just wanted to comment that I'm just going to say that's wrong. There is no time dependence of the dark energy. We're not the only ones that looked at this. But if instead of going after this, so here's the dark energy equation of state, it is an integral of the actual thing, the dark energy density. And so you can go after that directly. And if you do that, here's the cosmological constant. This is as a function of redshift. And then the data's binned, and we get 1.5 sigma discrepancy, that's all. And look at this, if you take their parameterization, it goes off way over here. And by the way, there's, after redshift of 1.5, there's only one data point, the Lyman alpha at 2.3 redshift. And so the reason you're seeing this bizarre behavior is because you can't parameterize properly if you only take those two terms at z equals 0. It's a bad parameterization. And you shouldn't be going after W anyway when you can just go directly after the energy density. So it's not there. And I'm not the only one who's saying this. Many people have looked at this. Okay, Hubble tension. We heard about it yesterday from Adam Rees. This one is interesting. If it is there, then it is very difficult to explain. As I said, we're in the era of precision cosmology. If you try to make any changes to cosmology after the CMB, it fails. There's a long paper about this, The Hubble Hunter's Guide by Knox and Malaya, which shows you why all of them fail. If you change one thing, you're going to change the other, and blah, 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 and then everything falls apart. So early time, before the CMB, you can do it. The way to do it is add an extra energy density. That will speed up the universe expansion so that the length scales are smaller. The sound horizon at the time you get to the CMB is smaller. And as a consequence, to keep the Doppler peak at 1 degree, which we know is true, the inferred value of H0 is larger. Now the question is, how do you put in an extra energy density? This is also not easy because things go wrong. So dark radiation goes wrong. My favorite is early dark energy. And in this one, I have a slide on it, but I don't think I have time, but I'll just say that what you have here is essentially a vacuum energy that's constant until you get to just before the CMB, it dives off, okay? It goes off, and by adding that term, that it becomes 10% of the energy density of the universe at exactly the right time to cause this speed up that I described. And then it has to go away. So this can be done, and it's not unnatural. I like this one. However, all of this is supposed to make the S8 tension worse, except now the S8 tension seems to have gone away very recently in the last few months. This is the amplitude of matter fluctuations on 8 megaparsec scales. How clumpy is the universe on these scales? There's a discrepancy between what the CMB experiments saw and what other more local experiments saw, but now there's this recent, I don't know if I have a slide about it, yeah I do. So they looked at, 125,000 galaxies, and they're finding now this thing, S8, that it is now in agreement with the CMB data. So it looks like this one's gone away. Okay, this one's really weird. If you take the DESI results literally and you get a negative, the best fit is a negative neutrino mass. Well, of course not. That's got to be an effective neutrino mass. So is that systematics, or is that the problems with using, they're using this, as I said, this BAO data, and the main thing they're doing is getting a new answer for the amount of matter in the universe. Okay, or is this a sign of new BSM physics? That would be fun. But then people argue about this a lot, and probably nothing there. I'm not sure. Okay, and then finally, the fact that the James Webb Space Telescope has found too massive and too many early galaxies. And so people said this is breaking lambda CDM. Because initially what they thought is that in order to produce a galaxy with this much stellar mass, that the efficiency of converting baryons inside this halo had to be 100%, which corresponds, this efficiency of conversion corresponds to a very large stellar mass in the galaxy. So these giant masses are not allowed in lambda CDM, it's too much, okay? But now, more recent analysis, the answer to a lot of these questions appears to be systematics, Anyway, so they looked at, well, in this case, they just looked at different galaxies and found this number is down by a factor of a third, which is still too high compared to today. You still have to explain it. But there are solutions, and one of them is that you start out with the initial stellar masses, how many stars with different masses, you change that. Instead of the canonical value that we have today, if you put a lot of if you put the mass in high mass stars instead of low mass stars, well, the luminosity scales is m cubed. So a single massive star produces a lot of light without needing as much total stellar mass. So this one has a solution. So in the end, I'm putting a no next to most of them. Time dependence of dark energy? No. Sigma 8? No. Negative neutrino mass? No. Too many, these things, too massive early galaxies. That can be, I think that can be explained. Hubble tension is the only one still remaining that we play with. And, well, you can see all the uncertainties in that, so we'll see what comes of it. Okay, so of course, what is dark matter, what is dark energy, or do we need a paradigm shift? Sorry, that was too long.
Show simultaneously. Check and Hooft. There we go.
We did not synchronize.
Because I will now ask you questions and you give your answers, and I will try to follow the slides as far as I can. So let me see if I can. It's going to be a bit small, but hopefully you can read. Okay. So the organizers posted all these questions for this conference to answer, and obviously we will not, but we try at least. We just go in order. So the first question was, is nature probabilistic or deterministic at the fundamental microscopic level? And please, Gerard first, and Frank after. And the others, if they want to say something on this topic, they can add their own. I want to do it question by question so that we don't have to repeat the question. That's the only reason. And hopefully we get an agreement, or the disagreements are evident. So what's your take on this first? Oh, no, please say that. So otherwise we will go up and down all the time. And I think we have to use
Does this one work?
it should work. Well, actually,
Oh, maybe not.
that works. And first you want to hear the question, right? Yes. Okay, so the first question is whether nature is probabilistic or deterministic at the fundamental microscopic level.
Well, I'm sure that they're not going to agree with this one. My take on it is that I can't find anything worse than a theory where various realities are somehow realized in a way which I don't understand. And I like to understand things. So I like to understand quantum mechanics such that it makes sense to me. And I say, of course, nature is deterministic in the sense that you can imagine that laws exist that are exactly obeyed by all particles and all phenomena that you see in this entire universe. The fact that stating that the laws exist doesn't mean that we can solve the equations. Far from it. We have to take every single atom in the universe and say exactly where it goes. That's totally hopeless. That is not the claim, of course. The claim is that these laws exist, and in fact, we can find out what they are. I don't see why not. What we cannot do is solve the equations. No way. But the idea that the equations exist makes lots of sense to me. So if it's showing us that it is dead or alive, not both. We know that. And so we know that nature's laws, if they are followed up correctly, will say, no, in this universe, or in this world where the past data are such, the cat dies. In the other world, where the past data must have been different, the cat will stay alive.
Okay.
And, so that is determinism, even though the cat can have still two possible fates, really. But
Okay, thanks. Let's go to.
Okay, well, it would be really nice to get probability out of the fundamental structure of physics, but I think very basic phenomena point in that direction, like radioactivity, the fact that at the LHC or other accelerators you can do the same thing over and over again and get different results, which Einstein said was the definition of insanity, to do the same thing over and over again and expect different results, but that's what happens. So nature is insane. I'd also like to say that quantum mechanics is less, as currently formulated, is less indeterministic than you might think. First of all, the equations for the full wave function are completely deterministic in standard formulations. Also, if you repeat an experiment over and over again, you get convergence according to the central limit theorem to a definite result, so the probability of a definite distribution. So it's a definite prediction for that repeated experiment. And then finally, I'll come back to it. So quantum mechanics has considerable determinism in it already, and but also the phenomena point to probability. Oh, the other thing I was going to say is that, of course, in quantum mechanics there are many straightforward predictions that are not probabilistic at all, like the ratios of different energy levels, the radiant corrections to this and that. These are perfectly definite consequences of quantum mechanics. So quantum theory is less probabilistic than it might appear on the surface.
Okay, so does anybody want to add something? Well, then the next question is, do we fully understand the quantum to classical transition? And this is Gerard's answer.
for me, this is the simplest possible question. There is no such transition. As clear as that. The theories, some of the things that if you make an atom large enough, it starts to be plastic. Well, if you build it up and then yes, but there's no transition, there's no halfway deterministic theory. The world is deterministic or not. There's no in between. So also there's no transition. The world is deterministic all the way to infinity.
Okay, so that's your view.
To me, the big question about classical to quantum transition is really the broader question of reconciling the strange world of quantum theories, this kind of probabilistic aspect and wavy particles and all that stuff, with our everyday experience, which seems quite different. So to me, to resolve all questions of observer dependence and things like that is really a question of convincing ourselves that we can model our experience within quantum mechanical formalism. And for that, what we really need, I think, is a more realistic theoretical physics embodiment of psychology. So we can point to the behavior of some entity within the wave function and say, gee, that's just like me.
So, like conscience.
Well, we would determine in the process, we would understand what consciousness is.
Very good. Well, so next question. Oh, unless somebody wants to come. No. What guiding principles should be taken as starting points for formulating physical theories? How do they change when we move from infrared to ultraviolet scales? The guiding principles. It's better if you look here, I think. Yeah, what guiding principles should be taken as starting points for physical theories?
Don't forget, you already have many laws of physics that we do know. From there, we can use every single instrument that we can get our hands on to see what else we can learn about the laws of physics. So symmetries are very important. They have been extremely successful machineries to figure out how particles interact. Much more so than ever expected before this way of looking at things became popular. And then, of course, unitarity just means that if you start with something that has total probability 1 not happening, then there's total probability it will stay 1 forever. That's, of course, a necessary condition. Whether you use a quantum mechanical, fundamental quantum mechanical description, or a fundamental classical description, you can do all three there.
Okay.
So that's
Frank, please.
So I begin by agreeing with the spirit of Gerard's initial response, which is that you have to pay attention to the fact that we know a lot, and these principles are embodied in what we know, and the fact they guided us to what we know. That's so powerful. So I think unless there's some compelling positive idea that motivates suggesting deviations from these principles, it's likely to be fruitless just to question them, although it's of course legitimate. If I had to guess, I would guess more symmetry, because that's pretty and nature seems to be beautiful, and it's been very successful in the recent past. And in some sense, when we go to new realms of the macro world, that's all we've got. I was surprised myself to say less causality. This is something that I took from this conference, that people have questioned causality, and there is a motivation, I think, for questioning causality in our present. And what does it mean to question causality? I think really it means questioning the initial value formulation of physics. That you should have, on the one hand, a set of fundamental laws that tell you how things develop in time, and on the other hand, quite separate hypotheses about what the initial conditions are. That seems very artificial, and we should anticipate the possibility that we'll have theories that tell us about correlations of events in space and time, but without that initial value formulation being possible. I also think that locality is suspect, because we're using the same notion of continuum that we got from Euclid, who worked with rulers that you could divide in half and smaller, but nowadays we know that there are atoms in a very different structure at short distances, so it's really surprising that we still use the Euclidean continuum, and that, I think, is also suspect.
Good. Any other comments on that?
The second half of the question is, do they change or move UV scales? Actually, that's an interesting point, because in fact, something like unitarity does have a very specific meaning. Has a very specific meaning on field theory. That's not the same meaning that it has in classical physics, and it's probably not the same meaning that it will have in a fully gravitational theory. The sense that you always get something out with probability 1 is general, but the specific nature of the idea is it can change as you change scales.
I could also mention one more thing that came up over coffee, actually, which is there are very direct tests of causality. That is, the hypothesis that operators commute at space-like distances. From those relations, you can prove that certain functions are analytic and then describe. dispersion relations. So, although it's not very fashionable these days to study dispersion relations, if you're interested in causality, looking for violations of dispersion relations could be one rigorous avenue to do so.
Okay. So our next question, or you want to add something?
Yeah, I want to add something.
Okay.
That causality is also a primary condition for primary agreement force. But what I want to add to what Frank is saying, that he mentioned doing repeated experiments and was surprised to get different answers that we only need quantum mechanical. But of course not, whenever you repeat the experiment, whether you like it or not, its path is totally different. The whole universe was in a different state. So to get another outcome of your experiment is not staging at all. And that these outcomes obey probabilistic laws is indeed what you should expect in any of these circumstances. So quantum theory, the way I want quantum theory to turn out to be classical, would also want the same thing.
Yes. I sympathize with that, and of course you're right, that if you repeat macroscopic experiments, there's no surprise that you get different results depending on the temperature of the weather and all kinds of things, and the earth is shaking. But what's unnerving, I think, is that even in very, very simple, idealized circumstances, you seem to get the same thing in same conditions with very good control. Probabilistic.
So what you think is idealized and simple is not at all simple. So that's just that you don't understand that. And I add the word yet, because I think there's no reason to think that we're going to find out how basic laws do work, and you can have a it's a very important question.
So we move on. So the next question is, which mathematical framework is best suited to build consistent theories that are applicable in unexplored regimes?
We should move to the next page.
I move to yours too, yes. Here we go. So first is Gerard. Yes, this is yours.
Well, I've actually written a book about that. That's a book is called Cellular Automaton Interpretation of Mechanics. And the cellular automaton is an ideal model for describing what I think is going on. And a model that would allow itself to be rewritten in quantum language. There I emphasized, like I did before, that quantum mechanics, to my mind, is a language to say how things work. So quantum mechanics doesn't give things that you can use to prove it to be right or wrong. No, languages, of course, are limited to our understanding. So languages of people living in the bush will not contain the words for automobile or telephone because that didn't exist. The same thing for quantum mechanics. It doesn't contain all the possible ways in which particles of nature can be formed because we don't know them. So nobody should be surprised that we have now a theory that we have to work with, which is not ideal in every aspect. And therefore it gives you deviating results all the time.
Oh, yes. So I said nothing presently available. And I think you would agree that your program has ways to go to be fully realized. But a coherent formulation of string theory might suggest a way forward. And it's a very rich collection of mathematical ideas there. At least some caricature of the world seems to be emerging. But there's no coherent. When I say incoherent, it's not clear what the axioms are. It's kind of a graph bag of tricks, and so it's not clear what the question is to which string theory is the answer.
Is a high energy scale invariant fixed point necessary for consistency of quantum field theory? Two negative answers. I can anticipate.
No, first of all, it's a very important idea to work along those lines. So to think that maybe gravity can be approached as a renormalized theory in certain descriptions, and that therefore you can make better predictions using quantum gravity. That's a very good idea. I don't think nature has to be like that, but it could be, and like so many other possibilities in our science, we have to check it. So this research has to be done, even though I'm not sure at all whether this will be whether this will work or not. It remains to be seen in the future.
Yeah, it's certainly not obvious that it's necessary, and I think there are lower dimensional models where it doesn't even happen if they're fully consistent.
Okay.
I would agree.
You agree with it? All right. And then, is there any strong indication and or real need for unification of all interactions? Do you believe
For
it's
me?
necessary to unify?
Unfortunately not, but in the past we love for a long time, we thought that weak interactions and magnetic interactions and strong interactions were all three totally different things. And then to our utter amazement we found that they all decided all along part of the unified theory. Except of course you can still change some relative strength and couplings, but otherwise this came as a surprise, and that surprise may again happen, but it doesn't have to be. It can always be that there are different kinds of forces which simply have to be added, and that will be the model. I wouldn't like such a model, but if it turns out to be true, I can like this up whatever I want. The model works, and then I have to accept that.
But maybe we're using the word unification in a slightly different sense here, because John said earlier that electroweak theory is not unified because there is because you have two separate couplings. You are saying that still you call that unified.
I was calling that they're intertwined, they're not the same force, but they're intertwined, and as such, you have to use the same mathematical techniques to approach them. So I think electromagnetism on one hand and electroweak theory on the other have much more in common than their differences. So indeed, there are ways in which are different, they're not completely different.
Okay.
Yeah, so I think there were very, very powerful circumstantial evidences for the desirability and probable truth of unification, at least of the electromagnetic weak and strong interactions. This is because if you take the standard model as it stands, there are a whole bunch of multiplets with different structure and very lopsided and funny hypercharges dangling at the end. But if you scale up the kind of symmetry breaking that we already know occurs in breaking SU2 cross U1 into the U1 of electromagnetism, just scale it up, you find that all those multiplets fit very, very nicely into structures like SU5 or SO10. So I don't think that's an accident. The other thing is, if you now address the question of the numerical values of the couplings, which are also different, you use the formulas of the renormalization group, you find that the strong interaction gets weaker, the other two interactions get stronger, and they seem to unify pretty well quantitatively at a scale that's close to the Planck scale. So that's an indication that this kind of unification almost certainly takes place for the three interactions, and also brings in gravity as a logical next step, if you like. There's even circumstantial evidence that we know everything we need to know in order to consummate that unification.
Okay. So John doesn't think that unification is very essential, but you want to add something?
Well, I just asked Frank's opinion about the argument that the logic of protecting it against that hierarchy indicates a problem now that we haven't seen any new physics at the 1 scale.
No, I think, well, this gets to be a complex question of detail, but I don't see any really significant problem. It was a big disappointment not to find supersymmetry at the LHC because that improves the quantitative unification of couplings. So I did say that there's also circumstantial evidence for low energy supersymmetry, but the nature of the evidence there is sort of logarithmic in energy scales. Might be that we're just a little bit too low for that, but certainly, but in any case, no, I stick by unification.
So this is a really interesting discussion, but since time is going quite fast and we have a lot of questions, I would ask you to be a bit more concise, perhaps, in the interest, if you can. So the next one is whether gravity is more or less or equally fundamental than the other interactions. And
Well,
I believe this.
I think the question is somewhat vague, depends very much what you call fundamental. I think in a way all forces are fundamental, but, and we treat them the same way. But it's indeed very like for others that actually Frank mentioned. I can just, I would follow him very well if he would say that it has been so successful in the past to realize that the forces may be all related, but it's not a bad idea to try that thing again. But in science, I think in science you have to also learn the lesson to be very careful with such suppositions. Maybe forces have different forces have different. But I would certainly be very much interested if someone comes with further arguments that they actually are different aspects of the same thing. So, it's completely basic, I don't know.
Well, this is a dangerous question in the history of theology, whether one or the other of the persons of the Trinity is supreme. I would just say that there's one structure and it has different aspects.
Okay. Now, another difficult one is space-time continuum at very short distances.
Well, that's a very interesting question because, well, from my point of view, it's very difficult to make any models where apart from time or any other quantity is continuous, because it means that real numbers would be following each other at infinite speed in the law of nature. If these laws of nature are realistic in the sense of itself, then it's very hard to imagine other numbers to be discrete. Like there are in our models today. In our model, not only time is continuous, but space is also continuous. Many other properties are also continuous. Angular momentum has completely lost, now it is fundamentally discrete. But I would suspect this kind of discreteness also to become a property of space and time. Whatever you mean by space and time, because that is also not clear at all in German descriptions and definitions. But once you have the definitions, I would suspect that nature should show the space-time and all the other continuous quantities in the world to be discrete after all. That makes a model finite. It's kind of finite, it's very needed physics. So this is what I would search for.
Okay.
Which doesn't mean that the other possibilities excluded.
I'll try to be very brief. The fact that the continuum concept that we basically inherit from Euclid has held up so long in spite of the very different understanding of nature we have today and atomic structure of matter is a miracle. I don't expect it to continue, and that's exacerbated by the fact that if you actually look at the mathematical definition of a continuum, it's very, very awful. You get involved in great subtleties of set theory and continuum hypothesis, which is independent of the other axiom. Anyway, it's very complicated, and I think nature should at some level be simpler than that.
Any other comment on this? Any way of measuring discreteness of space-time experimentally?
It presumably could lead to diffeomorphism violating interactions in the present theory, and it could do phenomenology based on that. When I try to identify stabilities, that could be challenging.
Next, what can black holes teach us about quantum gravity?
Well, I'll give a little talk about that.
Okay, so maybe
I claim that it is very useful and very promising to study black holes as well as we can. We can try to use all known physical rules to describe what non-trivial phenomena can be encountered, such as the singularities of a black hole, and to figure out how to handle those in terms of the theory we got. And the theories we have is, of course, in the first place, the standard model. Then we have Einstein's equations for the space and time, and there's a gap between which we don't understand. But the black holes themselves also contain a gap that you don't understand, which is basically the interior of a black hole, with analytic confirmation of the black hole. So if we manage to fill those with laws of physics, which are completions of laws of physics, that tell us exactly how black holes behave in a standard way, I think that is very promising. It's not completely promising. It doesn't guarantee that we will learn anything more, but it is a very important way in which to investigate, make investigations that have at least the potential of giving us very interesting properties that we can work on further.
okay.
I said it here, thought experiments about black holes might be very powerful in the right hands. And, but a problem with that is that different, very bright, capable physicists have been thinking hard about black holes for years now, and come to very different conclusions, even up to a factor of 2. So I think it would be very nice to get more experimental experiments about black holes, and I think that fortunately that's coming from gravitational wave experiments. Then we can have a richer, more informed discussion.
Some more thoughts on this?
Of course, I would agree. I think the main problem is how to understanding how the quantum scale would show up at, for example, the scale of the black hole that we are observing, which is a kilometer scale. There have been some ideas, including here from Gerard, but I think there should be more work to understand this because the scale is very macroscopic.
Okay, we're getting to quantum mechanics here. So the next question is the Hilbert space locally finite dimensional? Sorry?
Is Hilbert space quantum gravity locally?
I'm sorry, maybe I missed
No,
one.
I missed it.
Yes, you're done.
As I said before, quantum mechanics is really a language around that theory, and that includes Hilbert space. The classical theory with which I want to compare any model and that classical theory doesn't know about any Hilbert space. So there is no Hilbert space. But as soon as you use quantum mechanics to mimic that classical theory and you get exactly the same results in terms for all your predictions, then you may have used Hilbert space. But that Hilbert space might be a different Hilbert space depending on different kind of models you have in mind.
Mm-hmm.
So,
Okay.
Perhaps my answer is similar in spirit, that Hilbert space is a device, a framework for organizing a description of the world, and you can do it in different ways, at different levels. Certainly in laboratory physics, we typically work with very finite Hilbert spaces locally, but if you could ask a more specific question, we can try to address it. Maybe there's some time.
Is there a black hole information loss paradox? And Gerard says no.
There is perhaps a difficulty. The difficulty is to get the right equations to understand how the information is passed on. Well, in the theory which I described in my talk, the particles that are being absorbed by the black hole will not be traceless, they will leave something behind. That something behind can be exactly calculated. What I can do is that there is a signal in the outgoing particles that exactly matches the data that we're getting in. The danger is that to do this right is very difficult because gravity is makes no distinction. So if one particle drops into the black hole, the other is something solved. If the other particle drops into the black hole, it's a totally different particle, but it generates the same energy momentum tensor, then the outgoing signal will be the same, and that would violate unitarity. So here I have a problem in my hands, and the problem has to be solved. So it looks as if, well, from other perspectives, it seems rather easy to solve the problem. Just add a few terms to this illusion operator, so that it's unitary and everything will be solved. But that's not obvious. It's not clear how to do all this. This thing is still very, very in its baby phase. So we don't know anything. I don't think there's enough paradox.
Obviously, the situation, what I wrote here, obviously the situation seems paradoxical to many people, so that's a paradox. But I'm not sure how deep this paradox goes. Information, so the nature of the paradox is that you have evaporation of a black hole apparently into thermal radiation, which would be the evolution of what could be a pure state into a mixed state. But the small deviations from exact thermality can hide a lot of structure. And I think so I'm not sure how deep this paradox goes. It might be just that there are small modifications of the calculation that need to be done. And I think it would be very good to study analogous situations where we know what's going on and you have approximately, well, if you heat up a lump of coal, it looks like thermal radiation, but we know it's not if you think pure state. So how exactly does that happen? How exactly is that reflected in the radiation? I think the black hole might not be so different.
John has a comment.
All the discussions that go on about this assume that the black hole totally evaporates. I think it could be an opportunity for someone who's more clever to look at the arguments. There are arguments of why that has to happen. We'll look at arguments as a devil's advocate and see if we can poke holes in the logic of being forced to evaporate black holes, and maybe it could be recognized.
So continuing on a similar line, how do we describe the entropy transition from volume node to area node in gravitational collapse? Gerard first. This is your.
Yes, this is a question of counting states. So apparently, black hole models contain states, describe states the black hole can be in, and a very large black hole, for very small black holes, this number of states come out to be finite. And the question is whether the general area or volume is not well defined if the total number is finite. But for very large black holes, the number of states it can be in is not going with the volume. It goes goes slower than that, and the reason is that the larger the black hole, the lower the temperature of this radiation, so the particles involved with the same black hole do not generate as many states as the interior of the black hole would have if it would be avoided law. So yes, there's a law that tells you that the number of states is actually a property of the horizon of the black hole, and that horizon gives the same thickness no matter how large the black hole is. So the very large black holes, the area law wins in the volume law.
I don't have a lot to say about this, just the first remark is that it's not a violation of the second one, thermodynamics, although areas sound smaller than volumes if the coefficient of the area is big enough, it's okay. The more general remark is that I think statistical mechanics in the presence of gravitation needs to be refined because there's no equilibrium. So I think we need a more general form of statistical mechanics which talks about probabilities of different histories.
So it's easy to assess equilibrium and throw in something in it. And at the time it was a semantic picture.
Well, for a black hole in that particular environment, but for a general gravitational situations, it wouldn't be as hard to establish.
Next is a couple of questions on
Mountains is also unstable.
This is all the time with substances which are in equilibrium.
Next is about cosmological constant. Do we really need a dynamical explanation for a small cosmological constant? What is your thought?
Here, I am not sure.
Okay, then we can.
Sure, I think the cosmological constant is for one nature, but where it comes from is very mysterious to me. So I would love to see a better explanation.
But you think it's really a constant and not something dynamical? It's a fundamental constant of nature. That's okay, you answer.
It could be something dynamical, but that makes it a lot more complicated. You like to see simple models. In simple models also, the cosmological constant is also constant. So in complicated models and models which contain hidden fields all over the place, the cosmological constant would be space-time independent. That is of course not a constant. It would be a bit messy model, which I would try to avoid as long as I can.
So the question is, do we really need it? Probably not, although that might change with this Hubble tension. But it would be wonderful to have one. And maybe a sub-question that's more addressable, and I know of models that do address it, is the correlation between having a very small residual energy and it lasting a long time. So that I think is a coincidence that might be explainable.
I'm going to make a connection with dark energy. I mean, the cosmological constant is a bizarre problem in itself. Why isn't it 120 times larger than what we see? But the idea, maybe you could have driven it to zero, but to drive it to some small number, that's really, really bizarre. And so I'm not talking about the question of whether it's constant in time or changing the time. It's just where does that number come from? That's really strange, and we have to answer it.
And then, what is the real nature of what's called dark matter? And Mr. Toft doesn't know, so allow me to skip your turn. Frank knows.
Well, I pretend to know. So probably axions, almost certainly some kind of more or less conventional particle. I think there are many evidences that point out.
Well, or primordial black holes, they're interesting as well. But I mean, dark matter's there, and we do have to figure it out. It's really annoying problem.
You have a fixed theory.
Sorry?
You have a fixed theory your favorite theory, let's say.
Well, I didn't invent one like some other people up here, so I'm just gonna wait for nature has to tell us what's right. I mean, we have our theoretical biases, but that doesn't mean we're right, so we'll have to wait and see. The other thing that's interesting is we're assuming that it's cold dark matter in the standard cosmology. There are ways to test that. And so, for example, the shapes, the dark matter profiles inside structures like galaxies, if it is cold dark matter, then we know what that should look like. And it's an NFW profile, Navarro-Frank White profile. And although it may have been affected by baryonic physics in the late universe, the earliest ones probably would look like that. But then, so if you find something that deviates from that, then you can ask, okay, do I need self-interactions? Do I need to modify the standard picture? Another thing, thanks to Gaia data, is that we're seeing behaviors from the behavior of things. There are detailed measurements of locations and movements of stars. Well, the dark matter controls what those stars are doing. And so, for example, streams of stars, we have ideas where they came from, and the thickness of the stream can tell you about this central density of subhalos that would later produce the stream, so that we have many ways to approach the question of, is cold dark matter even right, or do we need to have a modification of that? Because both the, for example, axions and WIMPs are both in the cold dark matter category. So there's a lot of astrophysical tests that are only going to get better, and that'll help us learn something about the nature of dark matter.
Alessandra, you want to say something on this?
Oh, maybe I can just say, I'm very surprised that we have not yet actually understood what it is. That's despite all the effort which have been remarkable.
But axioms explain it. It's very hard.
Dark matter, by definition, it's not interacting with normal matter very strongly, right? And so that makes it hard to detect. Yeah, better be hard to detect.
Something happened here. Okay. Now here we go to something different. Do collective behaviors in biological systems have a quantum origin?
You said this. Oh, you
Sanders, okay. Yes.
Oh, no, but then.
Yeah, it's very important to know what a biological system is. How is it defined? And I really think that all biologists ever use to describe how biological laws work never refer to axis. So I'm sorry, I don't think there's any relation. Here, I'll sit on that. I've seen lots of people say the opposite.
I'm basically with you. There are some niche applications. Well, the first thing to say is that chemistry is based on quantum mechanics. So the very existence of molecules, reproducible properties, and so forth is based on quantum mechanics. And in that sense, biology, since it's based on chemistry, is using quantum mechanics. There are also a few niche applications in vision, where the quantum nature of light is very important. But I think for more delicate quantum behaviors, the biological bodies are a very unpromising environment. They tend to be at high temperature, they tend to be very unisolated, very messy. If you estimate decoherence times, they're very, very short. Probably.
Okay, they have something to add?
Well, I'm just going to make a joke. So when you have a kind of crazy thought, that's because something quantum mechanical happens in your head. Oh, it is the origin of free will, of course.
Well, here we go back to interpretations of quantum mechanics. Can we experimentally test or rule out interpretations of quantum mechanics and deterministic alternatives?
any case is going to be extremely high. But in principle, I don't see why not. So for instance, the standard model of the subquantum particles may be regarded as strongly supported by experiment. Now, not only that, experiment gives us something else. It also gives us constants of nature, or 20 constants of nature in the standard model that come just out of the air. We have no idea where any of these constants come from. We can't compute them. Okay, if someone comes to the air, usually that idea is chopped to pieces and used mass reactions. So that's not possible. But these numbers come from somewhere, and you could imagine that a program which has only just started could be more successful than what you ever expect, which is that you can find out models that contain all the forces that you know of, the standard model, gravity, all that, the discrete models. These models will not contain many real numbers or continua, and most topic forces that you can expect out of such models will be calculated or typically follow one over n exponential rules. That means that in any case, these constants, the possible constants that you can get from one will be for a discrete set, very likely. Although I know it will be but I think because of that, there seems to be a possibility that maybe these new models will actually be able to predict some of these constants, at least, or to be particularly rational numbers that would be understandable on our ways. In that case, this would be an enormously successful experimental confirmation of this interpretation of complex.
Okay, thanks.
Okay, add a two-part answer. One is that I think the best way forward is to continue to stress test quantum theory by applying it in new domains where it hasn't been tested so thoroughly. And one is the possibility of quantum computers, where we will be manipulating very, very entangled, complicated states in a richly structured way. Maybe something will go wrong. Another is gravitational radiation, which is a fantastic new domain, where I do think quantum mechanics has a role to play, as I mentioned. And then super accurate metrology. One way to see time is discrete, or if our notions of time are lacking somehow, is to measure it very, very accurately. Today, atomic clocks are pressing against part in 10 to the 20th accuracy. Maybe something will go wrong. So I'm much less sympathetic to Bell tests and things like that, sort of cuckoo clock tests of quantum theory, which are not stress tests, they're just telling you things you already know. That said, I think it would be quite good, even in that domain, to have quantitative, as John mentioned, quantitative strongman alternatives to conventional quantum mechanics in order to guide and interpret the results of experiments. So the experiments wouldn't just say that quantum mechanics is good, they would say this alternative is valid as quantitative measurement.
Well, this is not directly answering the question, but I just wanted to bring it up, the idea that fundamental constants could have time dependence that we don't know about, and people occasionally claim they found it, but these are interesting things to check for.
Okay, so again, I remind you that we are running late already. Yeah. So let's try to be quick on this. What can a quantum computer do for us, and how far are we from it? Now, how can we be sure? I mean, can I give a short answer to that? I don't know. But, yeah, quantum computer.
Here again, I would begin to stick my neck out, because normally speaking, quantum computers, one reason for selling quantum computers is that they are expected to be not only better than classical computers, but better in an exponential sense. The latter thing I don't believe. may well be a lot better than classical computers just because they use existing laws of nature more precisely than classical computers. So yes, they can be better. But this will not be an exponential law. So for instance, the problem of finding the prime factors of a large number will be done better by these quantum computers than a classical computer. But that will be a factor 2 or 3 less places. So if a quantum computer is discovered that they find the prime factors of a number of 1,000 decimal places, then I would say I will never cannot even dream of a testing system, no matter how its equations function, to produce the same results. So that would be a reason to say now theory of complexity, because this is some counter, very strong counter. If they manage to do that kind of technical very large numbers.
Okay, well, in the interest of time, I'll just refer you to my written answer, which I stand by, and if you want to ask more about it, either publicly or privately, I'm here.
So now we return to cosmology. Can we trust current cosmological tensions? If so, they can then teach us something about new fundamental physics. Katherine has already addressed that. And so do you want to say something on this? No, probably. Yes, if we're lucky, cosmology might help. Okay. Frank, you say no.
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 Well, with the possible exception of the Hubble tension, but I'm not going to get excited about that until the experts reach consensus.
Then can we probe pre-inflationary or pre-Big Bang physics? You don't know what it means, basically.
Well, pre-inflationary for sure.
Inflation. Well, this was such concepts are not well defined, so there are. Sorry? Yes, he has the microphone.
I don't think, well, I'm not sure that these theories of the Big Bang will work out that precisely. So I'm afraid that this is most not defined. So I'm tempted to say no, this is maybe implementing the possible.
I think, well, pre-inflationary, I don't think there's any question that we can make plausible guesses about model of behavior before an era of inflation. And that's done routinely in axion cosmology and other early universe cosmology. Until, however, we understand the nature of the Big Bang singularity or apparent singularity better, we certainly can't continue beyond that.
I don't know, I have vague things to say, but things that happen there are small things, Planck scale physics can be blown up, so you can look at it because of inflation. And so that there could be probes of, I don't know, non-causality, acausality, or something else that's going on that you can access thanks to inflation. And then people certainly are playing around with models for before inflation. This extra-dimensional physics with colliding brains and things like this. So there's a lot of attempts, but what I was talking about is where you can actually attempt to measure something.
Then how far in the past can we explore our universe using neutrinos and gravitational waves? You don't want to say anything on this? Okay.
Well, gravitational waves go way back. It's widely anticipated that there could be gravitational waves from inflation. There could be gravitational waves from cosmic phase transitions. Those kinds of signals would take us beyond any present-day observed signal, and I think it's extremely promising. But these would not be the kind of gravitational waves that LIGO would detect. They would be much longer wave. In fact, actually, the pulsar timing array says they have a hint of cosmic vacuum noise, which they ascribe to giant black hole mergers. The data will become more precise, and other approaches might give more powerful complementary information.
So first order phase transitions in the universe, it's like boiling water, but the other way around. So you have bubbles, and when those bubbles interact with each other, you get gravitational waves, and they are already, depending on the energy scales of when these phase transitions happen, they are already accessible to LIGO. For example, if you have a phase transition with the 8 GeV energy scale, then LIGO could see this. Now, also the 10 to the 8. And also the nanograv or the PTAs, the stochastic gravitational waves that have been detected, could also, an alternative description compared to the supermassive black hole mergers. The reason people are interested in alternatives is the supermassive black holes in the end have trouble merging. It's the final parsec problem. So if an alternative explanation also would be colliding bubbles from first order phase transitions, and the spectral predictions are a little bit different from the two, and it's hard to tell at the moment, but you will be able to. And this is active experiments of gravitational waves that are able to probe this physics. I also agree with Frank that this is one of the holy grails, is to please find that this is not something that any of the current gravitational wave experiments can do, or even this cosmic microwave background is going after the primordial gravitational waves that would be produced by inflation. In addition to the density perturbations, there are tensor perturbations that would give you gravitational waves, and we would love to see those, because that'll tell you about the scale of when inflation happened. It would be very powerful.
No, I wanted just to add the neutrinos start free streaming at 1 MeV, right? And the gravitational waves start at much higher, energy or shorter time. So they are the ones that will allow us to have really a snapshot of the universe at very, very close to its birth. So about the stochastic gravitational wave background, it's true that we are looking, with the cosmic wave background polarization, and it would be great if the Simons Observatory or LIBIRD will see something. But actually, this background does extend up to the frequencies of LIGO and LISA, etc. It's just that the omega gravitational waves at those frequencies is 10 to the minus 16, and these detectors will reach likely 10 to the minus 11, 10 to the minus 12, at the one that are planned also in the next decade. So we have to wait, but I think it will be fantastic if we will see one day this background at different frequency bands. And there could be surprises, because again, there are models that predict that the slope is not red, but it could become, blue in some frequency range, and maybe there could be some surprise. And then we will see, because the spectrum is going to grow at high frequency.
So
I agree with everything you said.
it's something that has already been discussed, but maybe we can briefly review the opinions here of the panelists. Would the detection of primordial gravitational waves be a direct evidence of the quantum nature of gravity?
Yes, just briefly, the whole concept of a quantum nature of gravity is not relevant at all. It assumes that such a concept, the question assumes that it means something. You can ask the property of gravity in many ways, and the most efficient way is to use Einstein's equations very often things are very large. If things are very small, you have to use the quantum language. And that includes, in the case of gravity, if you want to throw very tiny objects and not check their gravitational forces, it will obey quantum mechanics. So I think the question is going to be answered.
Right. Yeah, well, I've attempted recently to make this question precise in the context of gravitational waves. In quantum optics and more generally, the precise notion that replaces classical states is coherent states. Those are the states that have minimal quantum mechanical noise and where the field operators tend to act as C numbers. And precise formulation of the question of whether gravitational radiation is classical is whether gravitational radiation is described by coherent states. And I think the answer is that you can indeed test that hypothesis, and it's likely to break down in certain circumstances.
And then, can we detect a graviton?
In principle, yes, but in practice, probably not. The yes is, I can even tell you what I'm experimental could do in principle. That is, take a very strong magnetic field and have it a pipe with a very strong transverse magnetic field of light year or so length. Then you send photons in. The photons will couple with gravity because of the magnetic field. And then the photon will turn to gravity. Now you might put a screen there and take another light here or then you see the photons come out with the same force as you did. That means for a while these photons are being gravitons. And that will be a quantum effect.
Okay.
Yes. I think, well, as Gerard said, that the prospects of cleanly seeing a single graviton are very challenging, but the prospects of seeing the noise associated with quantization of the gravitational field, I think, are much more promising.
And I think this is the last question. How far are we from testing the quantum nature of gravity in the lab?
It's ill-defined.
That's my answer.
Well, if you keep going to my last slide, which I already discussed.
You had a scrap file, that one you referred to?
If you keep going, yeah. I think
There was a separate file.
Yeah.
Scrap. Yeah. You showed this already the other day.
So that's my answer. I agree. So it does agree with Gerard's answer that the question is ill-defined, but we can refine it. There are several different issues associated with how you treat gravity quantum mechanically, just as there are several issues associated with how you treat electromagnetism quantum mechanically, and there are different levels at which you can probe the quantum mechanical nature of these interactions.
Okay.
I won't repeat the detail.
So we've come to the end of this very long list. Alessandra has to leave now because she needs to go. Thank you very much for taking the time. And at this point I have to apologize to you, audience, because I failed completely as a moderator. You were supposed to be at this point half an hour ago, and there would have been time for your question. And the only thing I can say, my justification is that we've gone through many questions, and I assume that some of the questions that you may have asked have already been answered now. So, but if some of your questions were different from anything that has been asked until now, we have some 10 minutes for further questions from you. Sorry? There's no question. Well, let's wait a minute. Come on. Now I need a microphone.
Okay. And so thank you for the chance to go through all these answer the question. I would like to ask you what you think about the future perspective of particle physics and whether it is worth to essentially keep investing in large experiments, even building a large or super large LHC, and whether research in particle physics could be somehow also helpful for gravity.
I didn't understand the question.
The question is about the future of high energy physics, and more specifically, what the priority of building sort of successor to the LHCs. And I think it would be marvelous to have such machines, and wealthy countries like the United States or China could in principle fund such things easily, but whether they can be persuaded to do so, I don't know. Meanwhile, we didn't emphasize it at this conference, but there are many questions in what's traditionally called particle physics that still can be pursued. Some of them have moved over into cosmology, like the axion question, but the question of, for instance, proton decay, looking for electric dipole moment T violation, and several others are still available, even in the absence of big, expensive accelerators.
CERN is talking about building another accelerator, which is, how big is it? I don't know, big. And but the goal is, it's not really so much as to go into higher energy as to really study the Higgs, get more information about that. But there is talk about muon colliders. And now we're talking about something that would happen 50 years from now. And young experimental physicists are going to devote their lives towards trying to develop these ideas. And who's going to build it, I don't know. The United States is on pause, as you know. But so I'm pretty sure that CERN is going to do something. And I certainly agree with Frank, there's a lot of interesting questions you can probe in other ways. I was going to say something which I've now forgotten, but and a lot of those tie into cosmology, yes. And as far as the unification of forces, I'm agreeing with you there. I mean, it's too tempting because they seem, the three forces that other than gravity do seem to, the coupling constants seem to meet, or almost. And so, but how do you go after that? Well, the lack of proton decay so far is what killed SU5. But they're looking for other things rather than, you're not going to get a 10 to the 16, 10 to the 17 GeV collider, but there's other things that you could look for.
Other questions?
I don't think just remark that the problem with high energy physics is that we were too successful, so everything is fallen into line with expectations from the mid-1970s.
Hi, thank you so much for everything. Considering that in the next 50 years, we may find out about dark matter or not, we may find out about inflation or not. If you were a student just starting your career now, what would you do to prepare yourself for the future?
Well, I mean, the specific thing that I found the most enticing, sort of along that line, is that we have a rapidly expanding field of gravitational wave detection that's going to open up, I think, many opportunities, both in astrophysics, cosmology, and sort of numerical modeling and working with general relativity, and I think also quantum theory. There are many opportunities in quantum technology. That's a blossoming field. And I think another thing that I'm not sure I can assess properly, but machine learning is opening up. And there are also many new opportunities for positive opportunities to exploit the insight they give into large data sets, maybe respond to the great challenge of having quantum mechanics put chemists out of business. So all those. There are many. The problem is not finding something, it's choosing.
I'm going to say, I want to also add to that the data sets that are going to come from astronomy. So again, this Rubin Observatory that just started taking data as an example is going to have the biggest data set on Earth. So yes, machine learning is going to be a must. In fact, I don't think, maybe people don't know, but Jeff Hinton, who just won a Nobel Prize, he's also an astronomer now, you know. He works with my friends on because of these huge data sets sitting there. And you can learn so much about the universe, and the information coming in is going to be enormous. So working on the connection between the data and analyzing the data to learn about the universe, that connection with data and theory is going to be really exciting.
I guess the only thing I'd add is that you should plan to be flexible, because whatever you're going to do something for your PhD, but that's not what you're going to do for your life. So you have to plan to be flexible by reading way outside your comfort zone, and try little things on the side.
The other thing I would say is find something you love and you find yourself doing spontaneously. So explore widely and find what you fall.
This was very good advice. And there was some other question. Someone?
Because you partially mentioned this, but what do you think will be the impact of artificial intelligence in fundamental physics in the next future?
I think this has been answered to some extent, at least for cosmology.
Let me just tell you a recent experience I had. I was playing with new ideas for axion detectors using interferometry, and I asked a few leading questions to ChatGPT, and it gave me an excellent design. I think I'm going to be writing up soon.
Wow.
So I think the art of conversing with ChatGPT and leading it in fruitful directions by prompts that are appropriate, I think is going to be a very important skill for theoretical physicists and experimentalists going forward. So, practice.
Well,
and then when ChatGPT learns to ask questions of itself, then all bets are off.
Yeah, it's a very speculative question, I guess. Following on what Melissa was saying, let's imagine that in the next 30, 40 years, we actually measure and understand what dark matter is. What do you think would be the down-to-earth applications like society could benefit from? In the sense that, let's assume we understand this, and beyond the theory we like, not in the sci-fi direction, I'm not talking about algebra or this type of things, but let's assume we understand properly what this thing is. What do you think could be useful?
I don't see any direct use. And you could ask about fundamental physics more generally, or the last useful thing, which was not very useful, was probably the muon discovery. But that's not the point. I mean, these wonderful questions about fundamental science really stimulate people to develop new technologies. Also stimulate people to get trained in the technology. They don't necessarily continue to work in physics, but they learn things that they can use in the real world. think that's, that indirect effect is what we can not only hope for, but expect from these fundamental investigations.
Well, this is a joke. Because the journalists are always asking this question, and the answer Frank gave is, of course, you should give, but I'm just going to add to it. The novelist Dan Brown, who wrote the Da Vinci Code, in another novel, he was using matter-antimatter annihilation to power things, you know. So there you go. I'm joking.
Well,
for the record, I don't work on apply things.
It was angels and demons. Yeah.
But that kind of idea is a semi-serious idea, and an actual physicist named Robert Forward spent a large part of his career investigating the possibility of matter-antimatter drives, and they have some advantages. They can be very compact, give you a lot of energy. So I don't think it's necessarily so. They of course have to invest a lot in getting the antimatter in the first place. If compactness and lightness is at a premium, it might be helpful.
It is on a spaceship.
okay, so at this point we close this session and we have a coffee break, and let's thank our marvelous staff.